which means that the solutions to one are solutions to the other. So if an ordered pair satisfies one of those functions, then it will also satisfy the other two. These are the different forms we can put the same function in, and each one of them kind of tells us something a little different about the parabola. So if you look at your graph, when we graph x squared, James, can you shut the door for me, please? There we go. When we graph x squared, we have a point right here, so an anchor point at 0, 0, an anchor point at 1, 1, and an anchor point at negative 1, 1. So 0, 0 is the vertex of the graph of x squared. So the vertex is just what we call that point where the parabola turns around. So at the very top or the very bottom, depending on which way it's facing. When we transform the graph of x squared, the vertex always transforms to the vertex. So 0, 0 transforms to whatever the vertex of this parabola is. So what's the vertex of our parabola here? Nope. Yeah, it's 1, 8. Right, so again, the vertex is the point where the parabola turns around. So it's either the highest point or the lowest point, depending on which way it's facing. Can you find those numbers in any of our functions? Yes.
Well, in the first one, it has that x minus 1, which means it would go to the right one, and plus 8, which means up 8.
Good. So that point 0, 0 gets shifted to the right one, which gives us that x value of 1, and up 8, which gives us that y value of 8 for our vertex. So it's like we just shifted that point. We know that minus 1 is right 1 because it is inside the parentheses. So the way that you determine which direction you're going is through like order of operations. So if you imagine putting a number in for x, the first thing you would do is subtract that 1, and then you would square it, right? So any operation that happens before squaring it is going to be a horizontal transformation. And any operation that happens after you square it, like that plus 8, is going to be a vertical transformation. So then, what about the stretch factor? Any ideas? So one thing you can look at is if you go 1 unit to the right of the vertex, notice that this distance here is 1 vertical unit. So if you go 1 unit to the right of our new vertex, what is the distance between the vertex and that point? This distance right here is 2. So we took that distance of 1 and we stretched it by a factor of 2, so it became a distance of 2. So that's usually the easiest way to find the stretch factor from a graph, is just look at the point that's 1 unit to the right or left of the vertex. So we have a stretch factor of 2, which we also see right here in our equation. Right, so just like that 1 and 8 showed us transformations, to our graph, that 2 also shows us a transformation. It shows us the stretch factor, so how much it was stretched vertically or compressed, if that was the case. Does this function have a minimum or a maximum? It has a maximum, right? My vertex is the highest point on the graph. And that's because it opens down. And when you did your transformations, what made the graph flip upside down? So, but made it flip upside down would be a negative, yep. So notice again that we see that in our function as well, right there. So if our leading coefficient is negative, we know that the graph, not 1, 0, we know that the graph is going to open down. And notice that regardless of what form the equation is in, our leading coefficient is always the same. So that -2 doesn't change based on what form we put this in. So you can always tell if it's going to open up or down based on that number. What are my x-intercepts? Do we see those numbers anywhere in our functions? When you sit there and nod, it doesn't help any of your classmates know the answer.
You see -1 and 3.
Yes, where?
-1 in the f of x, and then 3 in the h of x.
So don't we also have the 1 right here?
Oh, yeah.
So that way they're in the same one. And that makes sense, right? Because we get x-intercepts by replacing our output with 0, setting our function equal to 0. And h of x is in factored form. It's a product, right? So if we set it equal to 0, that's the same as setting x minus 3 equal to 0, which would give us 3, and x plus 1 equal to 0, which would give us -1. So what about our y-intercept? What's that? Mm-hmm. Do you see that in any of our functions? Yep, in g of x, we have a 6 right there. Remember when we did linear functions, they had the form mx plus b, and that b was the y-coordinate of our y-intercept. So the same is true of all polynomial functions. If the polynomial function is in fully simplified form, so that it's just the sum of monomials, then that constant term is always the y-coordinate of your y-intercept. Because when you plug 0 in for x, every term that has an x in it just becomes 0, and all you have left is that 6. That is not the case with this -8, because if you plug 0 into that, x minus 1 is not 0, it's -1. So it doesn't make that first term 0 when you plug 0 in. So we can't just take whatever's added on at the end of any form. It has to be fully simplified, so no operations that can be done to simplify it further. Okay, so everybody to my left, your right. The right of the empty row, simplify f of x, and everybody to the left of the empty row, factor g of x. Okay, so to fully simplify, that just means to perform all the possible operations that you can perform. So in this case, we would want to multiply x minus 1 by itself, multiply that by the -2, and then combine like terms. Somebody over here, what did you get? F of x equals what? Holly.
-2x squared plus 4x plus 6.
Good. Which is just g of x, yeah? And then what did you guys get over here when you factored?
G of x equals -2, x plus 1, x minus 3.
Good, equals -2 times x plus 1 times x minus 3, which is h of x, right? So not only do these functions have the same graph, but they're actually the same function. They're just manipulated in different ways. So they're just written in different forms. So the rest of today, we're going to talk about these different forms and, again, the things that we can get from them. So there's 3 different forms of a quadratic function. The first one is general form, and that one is fully simplified. So you've done every operation that you can do so that you have the sum and or difference of individual monomials. So fully simplified. And if A is positive, so that A, B, and C, it's like the same A, B, and C that we used when we did the AC method to factor these guys. So A is always the coefficient of x squared. If A is positive, we said that the graph opens up. And so it has a minimum. So every quadratic has a minimum or a maximum, but it can't have both because it only turns around once.
What is 0? Yeah.
It's the parabola opening up. And if A is negative, then the parabola opens down, and so our function has a maximum. And we already noted that A is the same regardless of what form my equation is in. So they use the same variable for all 3 of those because it is the same number. Like if we take the same function and we write it in these 3 different forms, that A will always be the same, just like it was -2 in all 3 of our functions before. So, dang it. That's how big that was. So what we said about if A is positive and negative is the same for all of these. Doesn't change based on what form the equation is in or the function is in. And then my y-intercept, so we know you get the y-intercept by plugging 0 in to your function for your input. And like we said, when we're in general form, that just makes each term that contains a variable 0, so we're just left with c for the y-coordinate of our y-intercept. So 0, c. And then factored form of a quadratic equation is a product, right? So that means that there is no addition or subtraction outside the parentheses. So it's a product, all multiplication. No addition or subtraction outside parentheses. And from factored form, we can really easily get our x-intercepts because we get x-intercepts by setting the function equal to 0. And if we set a factored polynomial equal to 0, that's just the same as setting each one of the factors equal to 0. And x equals n. So we get m0 and n0. And then standard form is neither simplified nor factored. It's not simplified because I could multiply out that x minus h times x minus h and distribute the a to simplify it, but it's also not factored because we have that addition outside the parentheses. So the entire thing is not a product. The reason it's in this form is because it shows us those transformations that you guys looked at in that transformation activity you did the other day. The h and the k show us the shifts up and down and then left and right, and then the a is the stretch factor. So if we started with the graph of x squared, that would have a vertex at 0, 0. If we shift that to the left, or sorry, to the right by h units, then the x-coordinate of 0 becomes the x-coordinate of h. And then if we shift it up by k units, then the y-coordinate becomes k. The stretch factor doesn't affect the vertex because multiplying 0 by a will just give you 0 again, right? So that stretch factor causes a stretch through multiplying the y-coordinates. And so since our y-coordinate started out as 0, multiplying by a won't do anything to change it. So that's kind of nice because whatever your vertex is, you know it came from 0, 0, and it was always a result just of shifts, not ever of stretches. So our vertex is HK. So we will use these different forms of a quadratic function in a couple ways. So we can use them the way we just did to find information about the graph from the equation, but we'll also use information about the graph to write an equation for the function. And the important thing to notice is if you're given x-intercepts and you want to write an equation for your function, you're going to have to write it in factored form because that's the one that has like the x-intercepts in it already, like without any calculations done to them, right? You can just put those x-intercepts in. And if you're given the vertex, then you have to use standard form to write your equation because whatever the numbers are from the vertex are actually in standard form, so you can just substitute them. So when we write the equations for quadratic functions, we just have to be really careful to correlate what we know with which formula it's going to work in. So let's get some information from our graph. Turn your calculator upside down. That's not upside down.
What?
Turn your calculator upside down.
Oh.
Thank you. Because relating the formulas to the characteristics of the graph is kind of the point of everything we're doing today and tomorrow. If you graph it on your calculator, you don't really get to see how it relates to the formula, right? Like, all you're doing is just like copying, basically. And you know, there's a place for that, and it's certainly like nice to have graphs so that you can check to make sure that everything you found was true. But because you guys are headed to calculus, and calculus is the algebraic study of the behavior of functions, so using your function to determine the behavior, it's really important that we look at the relationships between the actual function as written as an equation and like the graph. So that's why I don't want you to just graph it on your calculator and then read it to me. So from that function, what are the coordinates of my vertex? Very close, but that 2, remember it's x minus h, right? So that would be x minus what? To get plus 2? You'd have to subtract. X plus 2 is the same as x minus negative 2. And then negative 9. One way you can think about this, like, so you probably notice, like, all the horizontal transformations, it's like they go the opposite direction that you thought they were going to go, right? And one way you can think about it is that if you're working with x values, if I knew the y value and I wanted the x value, I would have to do the opposite of all those operations to get x by itself, right? Whereas if I knew the x value and I wanted the y value, I would just plug the x value in and I do the operations that were given. So you always do the opposite operations to get x, and you always do the operations in the expression to get y. So all the horizontal transformations that act on x are going to be the opposite of what we think they should be, right? We see subtraction, we think goes left, but it really goes right. And then all of the transformations in the vertical direction, so acting on y, are going to be exactly what it seems like they should be from that subtraction or addition. So what about my vertex? Is that going to be a maximum or a minimum? It's going to be a minimum. Good. Because A is positive. So to express this in general form, we're just going to multiply it out. So we have f of x equals 4 times x plus 2 times x plus 2 minus 9, which is 4 times x squared plus 4x plus 4 minus 9, which gives me f of x equals 4x squared plus 16x plus 16, but 16 minus 9 is 7, so this will just be plus 7. So let's determine our intercepts from all of this. How do I get my y-intercept?
0, C from the general form.
Very good. So it's just the constant term of general form. And of course, if you didn't get that from the function, you could just plug in 0. I mean, like, you can always get the y-intercept of any function by plugging in 0 for x. So if you forget all these correlations, like, just remember that one thing. And then for my x-intercepts, well, I don't have this in factored form. I mean, theoretically, I could factor the general form, but if it seems like a pain to factor it, or if it's not factorable, we do need another way to get our x-intercepts. So another good way to find your x-intercepts is to use standard form. So if I take standard form, and I add 9 to both sides and divide by 4 on both sides, I just get x plus 2 squared equals 9/4. And that's just like an equation we've been solving the past couple days, right? I can take the square root of both sides. So we get the square root of x plus 2 squared equals plus or minus the square root of 9/4. So x plus 2 equals plus or minus 3/2. And then we'll subtract 2 from both sides. So x equals -2 plus or minus 3/2. And -2 over 1 is the same as -4 over 2, right? So -4 plus 3 is -1, so that gives me -1/2. And -4 minus 3 is -7, which gives me -7/2. Whoa. So we have -1/2, 0, and -7/2, 0. So now we can use all of these to sketch our graph. So I'll always start with the vertex, -2, -9. My y-intercept is somewhat unhelpful because it's like way up here off my graph, but we can put it up there anyway. And then my x-intercepts are -1/2 and then -7/2. And notice again that if you go 1.5 units to the right of the vertex, the y value is 0. And if you go 1.5 units to the left of the vertex, the y value is the same. So that's just the symmetry of the parabola. If you fold it vertically on the vertex, it's always going to match up. So any two points that are equal distance from the vertex in opposite directions have to have the same y-coordinate. So we could also say, if I go over 2 units, I should have a point up here at a y-coordinate of 7 because my y-intercept is 2 units to the right of my vertex. So I should have another point 2 units to the left of the vertex with the same y-coordinate. So then we can attempt to draw this guy. Make sure that your parabolas are round at the bottom. So we want these to be smooth curves, which just means that there's no corners. And that has to do with the derivative as well. So functions are only differentiable where they're smooth. So we want to be able to look at our graph and know if we'll be able to take the derivative or not. And we can tell by if it's continuous, and then also if there's not a sharp corner. So you just want to make sure your graph is accurate in that sense, that you don't have any edges where you shouldn't. So far, so good? Okay, let's write a function. So I want to find a function that has a graph with a vertex of 4, 1 that passes through the point 8, -7. So whenever I'm asked to find a quadratic function, the first thing I want to know is, do I have the vertex or do I have the x-intercepts? They have to give me one of the two. So in this case, they give me the vertex. And so what form of the function should I use? Yeah, we're going to use standard form because the vertex is right there in that equation. I don't have to do any calculations. So we're going to use f of x equals a times x minus h squared plus k. So my vertex is 4, 1, which means that h is 4 and k is 1. If you get those mixed up, just like x and y, they go in alphabetical order. So h comes first and k comes second. So f of x equals a times x minus 4 squared plus 1. So we're almost there, but we still need to know what a is, and that's where that second point comes in. That second point tells me that when x is 8, f of x is -7. So I can replace f of x. Remember, replacing f of x is not the same as replacing x. So I want to replace f of x with -7. It's not f of -7. It's this entire thing gets replaced with -7. It's not very good, negative sign. There we go. And then I want to replace my x value with 8. So a times 8 minus 4. It's one way to stop using your calculator. Smash it. And then we'll simplify as much as we can before we start solving. So I'll do 8 minus 4. And then 4 squared is 16. So I have 16a plus 1. Now we can solve for a. So we'll subtract 1 from both sides. And then divide both sides by 16, which gives me -1/2. And so the last thing to do is to just put that information back into my function. So we're going to take this guy, and we want f of x equals my a times x minus 4 squared plus 1. And that's my function. So that process will be the same, and we'll do some tomorrow, if they were to give me the x-intercepts, except I would plug the x-intercepts into factored form and then solve for a. So it's just a matter of which form we're using. Okay. If I say tomorrow on a Friday, you can assume it's Monday.
No,
Like,
it messed me up because I was like, wait, which day is it?
it is Friday. So on Monday, we will, do we have school on Monday? We do. On Monday, we will do the same type of problem, but we'll start with our x-intercepts. So then we'll just use factored form to do that same exact process. Over the weekend,